Okay, so now we are going to create a baby ROC curve. We're going to take those 3 points that we created on the previous page and plot these. So this is just going to be a demonstration ROC curve. We're not going to look at all possible values of pi 0. We're going to get Proctor Logistic to do that for us. But let's just plot our points. So we already know that if pi equals 0, then the false positive rate is 1 and the true positive rate is 1. So if we put a point right here, this is where pi 0 is equal to 0. Right? That's where we're using 0 as a cutoff for our predicted probabilities. Similarly, when pi 0 is equal to 1, we already know that we have a true positive rate of 0 and a false positive rate of 0. So on our graph, we can put that right down here. Right? So this is pi 0 equals to 1. And then we had one more point on here. And our one more point that we calculated was when pi 0 is equal to 0.5. That's the first thing we calculated. We had a false positive rate of 0.4 and a true positive rate of 0.55. So false positive rate of 0.4 and a true positive rate of 0.55, and I'm just eyeballing it here. So, and this is where we said pi 0 is equal to 0.5. And now what we can do is simply connect those points. So if I retrieve my handy straight edge here, I can connect these points that I just drew on here. See, it's not a straight line. It's not too far off a straight line. But remember, for this, we don't really want a straight line. But this is our receiver operating characteristic curve. And I will also put another line on here. Remember that the line of just random guessing this is our line of random guessing. And don't forget, so this is 1 minus specificity. That's the same as the false positive rate. Sensitivity is the same as the true positive rate. Okay. And just look at this plot that we just drew. Again, this is just a sketch of an ROC curve because we only use 3 points. But it doesn't look like it's going to be too strong of a curve, right? Because again, we don't want an ROC curve that is close to this line, and this is actually fairly close to the line. So how can we compare these curves? If we look at several different ROC curves, how can we compare them to know which model? Because for each model we fit, we might get a slightly different ROC curve. So how can we compare these to know which model is actually predicting better? Sometimes you can do it visually, but other times we need a quantitative statistic. And that quantitative statistic is the area under the ROC curve. We know that the total area here is 1, the total area in this box, right? So what area is under the random guessing curve? That goes right up the diagonal. So we know that there's 0.5 of the area is below this random guessing curve. Okay. So if we calculate the area under our ROC curve, we can compare that to the random guessing curve. And that's basically what I'm saying down here. I won't read this whole thing to you, but just to tell you how we're going to use the area under the curve. Better models have ROC curves that are closer to the left and top edges of the unit square. So up here, again, this is what we're aiming for. That's the point we're aiming for. So if we get this point, if we have an ROC curve that goes like this, we'll have an area of 1, right? So ROC curves with areas closer to 1 are better. So we're going to use these area under the curves to interpret our model and how good our model is. So how do we interpret it? This is sort of the way we used R squared in linear regression. But R squared is based on a sum of squared deviations. But since we're using maximum likelihood estimation, we don't have a direct R squared. There are ways that people have come up with calculating something like an R squared. But this area under the curve idea is actually a little bit better, I think. So we're not going to use R squared as our summary. Instead, we're going to use the area under the curve. And how do we use that? Well, the interpretation of the area under the curve is a little tricky. And it's a probability. And if you were to take a random pair of observations such that one of those observations had y equals 1, that is, one of those, if we did this with the Donner Party data, if one of those observations the person survived and the other one had y equals 0 or the person died, then the area under the curve represents the probability that our classification model would actually find the person who survived. They would have the person who survived would have a higher predicted probability than the person who died. That's what the area under the curve is actually telling us. Okay. I'm not going to ask you to interpret that on an exam or anything. But again, the area under the curve gives the probability that the model correctly ranks these pairs of observations. So it's going to correctly pick the person who survived. If the area under the curve is 0.5, then our model is doing no better than random guessing or coin flipping. Okay. So the scale for interpreting the area under the curve is a little bit arbitrary, but here's one that's often used. So if the AUC is 0.5, that means you're basically flipping a coin, so the model's not helpful at all. If it's between 0.6 and 0.7, or I'd say between 0.5 and 0.7, it's actually a poor model. So this should actually be 0.5 and 0.7. If it's between 0.7 and 0.8, it's acceptable or a fair model, and that's where, unfortunately, a lot of models end up falling, and a lot of models in the health sciences fall in this range. We'd really like to see areas under the curve of 0.8 to 0.9. That means we're getting pretty close to that upper left-hand corner of the curve. And if we're greater than 0.9, that's a really good model. That means we're really close to that upper left. So again, we're looking for areas under the curve, ideally greater than 0.9, more realistically between 0.8 and 0.9. And we can actually get SAS to do this for us. So in SAS, I'm actually just going to ask for the ROC curve by say plots equals ROC. So let's do that. Going back to my Donner Party data here. Up here's my logistic model. I'm just going to add plots equals ROC. See what that gives us. If I run that, you'll notice, so here's my ROC curve. On the x-axis again, 1 minus specificity, on the y-axis sensitivity. Okay. And I've reproduced this in the notes, so let me jump back to the notes here. Here's that same picture. So remember that this point is the same as using a cutoff of pi 0 equals 0. This 0, 0 point is the same as using a cutoff of pi 0 equals 1. And our point that we plotted was about 0.4, 0.55. So it was somewhere in this area. Maybe it was this point, I'll say. And this is approximately pi 0 equals 0.5. But notice that this curve now has more points than our little curve of 3 points did. Because this is using pi zeros all the way from 0 to 1. And notice that the SAS output also provides the area under the curve for the model, 0.6810. So what do you think? What does that mean? If we look up at our chart up here, 0.6810 is pretty close to acceptable. It's just a little bit below acceptable. So I would say an area area under the curve of 0.68, I'd probably say it's fairly poor. It's almost acceptable, but it's still fairly poor. Ideally, we'd have something bigger than that. So that means that given a random pair of people, specifically from the Donner Party, one who survived and one who died, our model will correctly pick the survivor about 68% of the time. That's the interpretation for the area under the curve. But really what you need to know is just that higher area under the curves are better than lower area under the curves. That's the end of these notes. I want to show you one more thing. And just one more thing that you can get from SAS. Actually, there's two more things I want to talk about quickly here. One is we can ask for something called the OutRock data set. I'm just going to call it my ROC. We call these rock curves, by the way. And I'm going to print that data set, my ROC, just to show you what this gives us. It's a way of looking at the data that are underlying this ROC curve. So the ROC curve will use predicted probabilities, all the predicted probabilities that are in our data set. And remember that the only explanatory variable that we had in here was age. And it turns out there are 21 distinct ages in our data set. So there are 21 distinct predicted probabilities. And you can see that for each predicted probability, it calculates the number of positives using that predicted probability and the number of negatives, and it uses that to calculate the false positive rate, the false negative rate, the sensitivity, 1 minus specificity, and of course these are the things that get plotted, sensitivity and 1 minus specificity. And so you can see that these are your pi zeros over here, or these take the place of the pi zeros, and this is the plot of the curve that you see in the notes. That's where that curve comes from. It calculates the sensitivity and 1 minus specificity for each predicted probability within the data set. Now the last thing I want to tell you, if you've gotten this far in the notes, then I have a little bit of an Easter egg for you, if you're interested in this kind of thing. On Moodle, under 9E additional resources, I put a paper from a recent rock curve study that I worked on in reproductive health. A lot of my research is in reproductive health, and we have a lot of data still available from that study. And the PI of that study, the principal investigator, is just dying for somebody to analyze those data. So if this is something that you're interested in, and you've gotten this far in my videos, please feel free to talk to me about this. It's possible that we could set up an undergraduate research study that you could work on. I have lots of data from leftover from that study that we would love to have analyzed.